Hello everyone. In this video, we are going to talk about z-score versus t-score and z-test versus t-test. So we're also gonna look at the t-distribution or the student's t-distribution. So what is z-score? Z-score, or we also call it the standard score, shows how many standard deviations any data is away from the average. So if the data is x bar and the average is mu and the standard deviation is sigma, then x minus mu over sigma is your z-score, right? So this way, if you have different distributions, let's say for instance different normal distributions with different mu's and different sigmas, this transformation, this linear transformation, will convert all of them to basically have an average of 0 and a standard deviation of 1, which we call them the standard normal distribution, correct? So let's say you have one normal distribution that is like this, for instance. So this is the mu, and then this is like mu plus 3 sigma and minus 3 sigma, which we're going to talk about. And then you have another one that is like this. And then you have another one that is like this, and so on and so forth. So they have different mu's, different sigmas, right? And because we are subtracting each data from the average, so the average of the data, the average of this new distribution, so I'm going from x to z, the average of z, the mu for z, is going to be 0, while the mu for x is just mu. And since I'm dividing by sigma, then the sigma for z is going to be 1, okay? So this way I can kind of, we call it normalize or standardize your measurements or your distributions, so we can compare one against the other, okay? So this is very common. We use it a lot in engineering, in machine learning, and so on and so forth. So that's why we want to talk about it. For instance, let's say there is a population of people with an average height of 170 centimeters and a standard deviation of 10. If you have a height of 185, what is your z-score? Well, simply 185 minus 170 over 10 is 1.5. Now, what's the meaning of this 1.5? Means you are 1.5 standard deviation away from the average, okay? And you might say, okay, what does that mean? So I'm 1.5 standard deviation away from the average. What does it implicate? What's the meaning of that? So here we're going to look at a normal distribution. In a normal distribution where mu is 0 and sigma is 1, you can see that basically half of the data are on the left side of mu, half of them are on the right side because the normal distribution is pure symmetric. But now if you move away 1 sigma, so your z-score is equal to positive 1 to the right of the average, or you move 1 sigma to the left of the average, z of negative 1, then the amount of data that will be underneath this curve, the area under the curve, is basically about 0.34 plus or minus. So what does that mean? Means if half of your data are falling from negative infinity to mu, then if you go 1 standard deviation away from it, 50% plus and minus 34%. So you can go to 84%, or you can go to like 16 or 59%, 15.9%. So in this case, let's say the height of the person was 180, okay, instead of 185. So the z-score was plus 1. So if I ask you this, if I go ahead and look at the heights of all the people in this population, how many of them are less than or equal 180? So I want to know the probability of the height of any person being less than or equal 180, right? What percentage of the people have height below 180? uh, 180 centimeter, not degrees, sorry. So the chance is, you say, well, since it's less than z plus 1, so I need to calculate it anywhere from negative infinity to z of positive 1, and you see the chance is what? 0.841. 84% of the people are below this height. Now, if I say, what if the height was 190? So if this height was 190, then how many people would be a height below that? So now your z is 2. So now you have to go to plus 2 sigma away from the average. And if you calculate it, you see now the chance is 97.7, right? So all I need to do is to say heights below 190, and there we go. And if I go to 3 sigma away, then it's almost 100%, almost. Now, you know this distribution goes to positive and negative infinity, but literally the area under the curve almost goes to 1 at mu plus 3 sigma, and it almost goes to 0 at mu minus 3 sigma. So that's what they say. The chance of you being in a normal distribution is either 0 to 1, as long as your data is mu plus and minus 3 sigma. These are almost any data that you would see. So in this case, the mu is 170 plus minus 3 sigma, so you're looking at 140 to 200. So the chance of the height being between 140 to 200 is almost 99%, 99.9%. There is very, very, very small chance that you are plus more than 3 sigma away from the standard deviation. Where does all these numbers come from? If you're asking, where does this 99, 84, these come from? They are coming from the formula for a normal distribution, which is for average of mu and standard deviation of sigma. This is the formula for it. Okay, and all I need is to find the area under this curve from negative infinity to some arbitrary x, correct? Which we call it the cumulative distribution, or we call it the, instead of PDF, we call it CDF, cumulative distribution function. And that is the probability being less than z, which is exactly this area that you see here. And those numbers, which we call the z-scores, those are also shown for you over here. So if I want to read off of this table, this z table, let me show you. So if your z is 0, which means you are exactly below at the average, then 50% of data, they have values less than z of 0. Now, if you go to 1 standard deviation, z of 1 plus mu, now you're looking at 84.3. You go 2, you see, you go to 97, you go to 3, you get more and more and more and more, okay? So you see exactly. Now, you might say, what are these columns represent? These columns are the second decimal. So, for instance, sometimes you don't want to know 1 standard deviation, you want to know 1.05. So if you are at mu plus 1.05 standard deviation, where do you get that? Because if you look at these numbers, they only have the first decimal. But if I want 1.05, I say, well, this is 1, and then this is 0.05, so I come here, and my number is going to be 85. Okay, so these are, the rows are the first decimal, the columns are the second decimal, and I have all of the z-scores. In MATLAB, if you want to get these numbers, all you need to pass to it is the command z-score. And it is going to basically calculate the integral of that function from negative infinity to your given x, and that is going to be the z, or basically the number from these tables. So this is how you read the z values, and these tables, as I said, we call them the z tables or standard normal distribution tables. Okay, and that's the physical meaning of it. Now, if instead of comparing a single data against the mean of the population and getting a z-score, you have a whole sample, you have a bunch of data, and you want to compare the average of the sample against the average of the population. So you want to compare X bar of the sample against mu or mu naught in this case, and you know sigma, then because you have more data in a sample, instead of one data you have n data, in the denominator you have to divide sigma by square root n. Okay, yeah. So because you know that if you define a new variable, whatever you want to call it, let's call it, for instance, I don't know, let's say capital X, this is X bar, then the average of this new variable is going to be mu naught, but the standard deviation of this variable is going to be sigma over square root n. Okay? And that's why basically getting a sample and having more data in the sample will reduce my standard deviation, correct? So if you compare this against a single number, the single number distribution is something like this, for instance, where this is mu or mu naught, and you have some sigma, but if you look at the distribution for the average, it is going to be something like this. So it has the same average, but clearly the sigma for it is much smaller, and I can say the uncertainty is smaller when you look at the sample rather than a single number. Now, before we go to t-score, there is one thing that I need to emphasize. So far when we talked about the z-score, the distribution that I have been using was normal distribution. And you might say, well, can I only use the z-score if my data are normally distributed? The answer is no. Z-score can be defined for any distribution that you want. So your underlying data distribution should not necessarily be normal. You can still define a z-score. But these meanings that I drew for it is 99%, 84%, and so on. These were all done using a normal distribution. So if you want to get these different, get the different distribution and use it for that, then all of these numbers in this table and the meaning of these probabilities, everything have to be basically defined, right? Because if your data is skewed to the left or right, or the kurtosis of the data is different or anything, then all of these numbers would change. So everything that we said was using a normal distribution, but guess what? You can define it for other distributions as well. Now, what is t-score? T-score is very, very similar to a z-score. Use it for a sample. The problem is, in this time, you don't know the standard deviation of the population. All you can do is to replace it by the estimate, which is a standard deviation of the sample. So here you use the standard deviation of the sample, S, instead of sigma, and you calculate the what we call t-score. Okay? Now, you might say, why do we call it t-score? If they are almost identical, you replace sigma by S. Why do you call it the t-score? Because they are almost the same thing. The reason is this. As I showed you, if I look at this entity here, and if I look at the distribution of it, if the data that we calculate the X bar from, if the data were normal, clearly this Z is also going to be a normal distribution with mu of 0 and sigma of 1. Okay? But if I use the sample standard deviation and look at this distribution of this number, which we call t, the distribution of this is not going to be exactly a normal distribution. So the distribution of this variable t is going to follow what we call the student's t distribution with n-1 degrees of freedom. And n is what? N is the sample size. And you might say, what is student t distribution? Well, if you look at the student t distribution compared to the normal, so this is the normal distribution, okay, this kind of lighter pink. Then these purple ones are t-distributions for different degrees of freedom. So this one is for t of 5. This one that is a little bit sharper is for t of 13. And as degrees of freedom gets bigger and bigger, ultimately they are going to be as sharp as a normal distribution. Okay, so your t distribution in limits, when you have an infinite number of data in your sample, ultimately becomes a normal distribution. But you see that the tails are heavier. So in the middle, it's not as sharp. In other words, the kurtosis of a normal distribution and a t distribution are different, right? So if you calculate kurtosis for the normal distribution, it's going to be 3. For the t distribution, it is going to be 3 plus 6 over nu minus 4. Where here in this formula, this nu is your degree of freedom. That's the same as this df. Okay, and you see that as this degree of freedom gets bigger and bigger, because the sample size is getting bigger and bigger, ultimately the t distribution kurtosis becomes the same as the normal distribution kurtosis, but always the t distribution has a bigger kurtosis than the normal one. So what is the probability density function, PDF, for a t distribution? Remember, for the normal distribution, it was this exponential function. For the t distribution, it's different. If you look, it's basically a power function here, and then you have 2 gamma functions here. So it's a little bit more complicated. The formula for PDF of t distribution is more complicated. Again, nu here is your degree of freedom. So for different nus, you're going to get different formats, of course. And t here is your parameter. Of course, again, the integral of this f of t from negative infinity to positive infinity should be 1, right? Because that's the condition for being a PDF. But this is the formula. And if you look at the t distribution, it only has 1 parameter. So t distribution has only 1 parameter, degree of freedom. The standard deviation, on the other hand, has 2 parameters, the average and the sigma. Okay? So t is a little bit, in terms of parameters, it's less, but the shape of it is more complicated. It needs this gamma function, which you know it's kind of a more generalized version of the factorial function, as you know. And this is the t distribution. Now, similar to z tables, of course, we have t tables. Here in the t tables, you can see that the rows here correspond to the degrees of freedom, df or nu, and the columns corresponds to p-value or alpha in this case, if you will. And for each one of them, you can find what we call the critical t-value, which we're going to use next for the t-test. Okay? And from the z-tables, we can find the z's that we can use for z-tests. Next topic is going to be z-test and t-test. But before that, let me re-emphasize some important thing. When do we use the t-test or t-score? This is when we don't know sigma, or when the sample size is small. So if the sample size is small, we cannot use the z-values. Okay, even if we know the sigma. But if the sample size is very large, we can, and we know sigma, then we definitely will use the z-score. But if we are dealing with the small samples, and if we are not sure about the sigma, and we can only rely on the standard deviation of sample, we definitely use a t-score. And let's look at the single number here. So let's say you have a sample of 15 students that they have an average of 82 on a test. So the average of the sample is 82, n is 15, and the sample standard deviation is 5. We know that on average, the population is on 80 on this test. We collected a ton of data, and then if we want to find the t-score based on this formula, the t-score is going to be 1.55. Okay? So this is how to calculate the t-score. Now you might say, why would you calculate z-score or t-score? You showed us how we calculate them. What's the application? Where would you use it? This is where we have to talk about the tests. So here, first, we look at the z-test. Okay, so here we are going to look at a z-test and see how we use the z-score. So what do we do here? It says a manufacturer produces steel rods that we know their standard deviation from tons of data that we gathered over time is about 0.4 mil, the standard deviation for the length of the rods. And the goal is the average length for these rods should be 50 mil. So the manufacturer should really shoot for 50 mil length of the rod. That is what we really want. Now you go and do some quality control. You pick 25 rods made by this company and find that the average of the length of these rods is 50.2. The question is this deviation really significant? In other words, are the rods that the company making really kind of longer than the desired length or shorter than that, right? So there is a difference between the ones that are made and the one that should be made. And here for the alpha significance level, we pick 0.05. Okay, so here this is basically what we are doing is quality control. Because if we are making rods that are longer than what it should be, then we should definitely go ahead and change our manufacturing parameters, right? Maybe a time that the rods are being cut, we need to shorten that in this case or something. So what do we do? In this case, since we know sigma, then we go ahead and use the z-score. The average of the sample is 50.2. The average of the population we should shoot for is 50. The standard deviation of the population we know is sigma, and since it's a sample, we need to divide it by square root of n, which is 25. If we calculate, we find that z is 2.5. This is the z-score that we found through the sample. Now, with a 0.05 significance level, for a two-tailed t-test, we find that the z-critical is plus minus 1.96. And you might say, where did you get that one from? What's the meaning of this 0.05 when you go back and look at the z table? But because here there is no alpha. Here you only have the first decimal and the second decimal. You might say, are these rows the alpha? No, they are just the second decimals for the z values. So what's the meaning of alpha here in this table? When I say alpha is 0.05, and then I say it's a two-tailed t-test, we know because it's a two-tailed t-test, I have to use half of alpha. So I should really look at 0.025. So now I should find the z at which the probability of the data being less than this z is what? Is 1 minus basically 0.0025, which is basically 975. So I should find at what z the probability of data being shorter than that z is basically 97.5%. That is going to give me what we call the critical z. Okay, so if I go to the table and I look at for the number that is 0.975, right? So look here. This is 0.977, that is at 2. So I need 0.975, and if you look at it, here that number is exactly 0.975, and if you look at what z-score it corresponds to, it's 1.9 and then 0.6. So the z should be 1.96. At 9.6, your probability is about 97.5%. What does it mean physically? Let me tell you the physical meaning. The physical meaning is this. The physical meaning is this. If I want to know basically at what length 97.5% of the rods that have been made are less than that length, I need to go and find the z-score. So I say, well, look, the z-score is that 97.5% of the rods are made shorter than that. The length of that, if I want, I can go ahead and plug here. Instead of 2.5, I plug in 1.96, and I have this 0.4, this 25, 50, and from here I can find the length of the average of a sample of 25 that has basically 97.5% of the rods made shorter than that. And let me calculate that number for you. That number is 50.157. So if the average of my sample is 50.157, then I can say that ideally 97.5% of the rods ever made should be shorter than this. But the one I'm making right now are even longer than that. They are 50.2. What is the chance? What is the chance of seeing? What is the chance of seeing some factory making rods this long? It says, hey, look, the z-score for it is 2.5 instead of 1.96. That means it's very, very rare. Now, how do I know it's very rare? So if I want to go and find the p-value in this case, I can, instead of that 1.96, I can look at 2.5. Let's go back, look at 2.5. So look, this is 2.5, and you see that the z-score for it is this, right? 9938. So what does 9948 mean? 9938 mean? It says if your length is this much, 50.2, then it is longer than 99.38% of the rods ever made. So the chance of you seeing anything longer than that is really 1 minus this and times 2. That is going to be your alpha, in this case the p-value. So if you subtract that, you are going to get 0.0124. So it's very, very unlikely, even less than 5% chance that you ever see such rod with this length. Okay, so you see my p-value is less than alpha, or my z statistics value, 2.5, is bigger than the z critical. Therefore, I should reject the null hypothesis. And you might say, what was the null hypothesis? The null hypothesis was that in this case, this sample has no difference, no significant difference from the average of the population, which is 50. But I should reject that. No, this is not the case. These samples are clearly longer than. These guys are clearly longer than what you are making. The chance of seeing anything this long is only 1%, not even 5%. So these are really rare. And because they are that rare, clearly you are making long rods, and you should go ahead and change your manufacturing parameters so you bring them down below which number? You're right, below the this number here. If your numbers are below this number on average, then I can say with 5% rarity case or type 1 error case, I can accept them. Okay? But as long as you pass this number, guess what? I'm going to say that you are making them too long. They are not good. You have to make them shorter. So you see here, we can look at all these different things from the z-score. Now, similarly for t-score, let's say your company is manufacturing some new alloy for aerospace bolts. The design specification says that the mean tensile stress of your samples should be 750. This is what you should be shooting for. This is your mu. Do you know the standard deviation of these bolts? No. In this case, I have no idea what is the sigma. Why? Because in this case, I don't have enough of data to calculate sigma. And you might say, if you don't have enough of data, how do you know mu? Right? Because mu and sigma are coming from the population, not necessarily. The mu does not come from the population all the time. Mu, in this case, is the design specification. Mu is what you should be shooting for. So for mu, sometimes you don't need to know all of the data in the population. For sigma, you absolutely do. But for mu, that could be just what you're shooting for. So now the engineer doesn't know the sigma. Sigma is unknown. So all I can rely on is the S from the sample. So the engineer goes ahead and takes 12 bolts and measure their tensile strength. And these are the number he comes up with. You want to know that whether the tensile strength of these 12 numbers in the sample are statistically different from the desired value of 750, and we want to do a t-test and a two-tailed one-sample t-test. So we need a t-score in this case. So what do we do? First, we calculate the average of this sample. That's 750.33. It's a little bit bigger than that. And you might say, well, that's not a big number. It's just 0.33 meg. Well, it depends. Although that's small, but for some applications, that could be significant. So here we calculate the standard deviation of the sample also. That is going to be 2.87. The number of data is 12. So we calculate the t-score, x bar minus mu over s over square root n, and that number is going to be 0.398. Now, is that number significant? Here, we have to go look at the table with n minus 1. So your degree of freedom is n minus 1 or 11. And for 11, we are going to see what kind of t-critical we get. And we, of course, need some significance value. So we pick alpha of 0.5 like last time. And we know for 0.05, since it's a two-tailed t-test, we have to use half of that. So we go and look at the t-table for 0.025. And with degree of freedom equal to 11, let's see what t-critical we can get. So this is 0.025 and this is 11. So we go here and we go here, and the number we are going to find is 2.201, right? And that is exactly this number that you can see. Now here we see our statistics t is much, much smaller than the critical t. So we cannot really reject the null hypothesis. In other words, we cannot say that these samples are made stronger than what it should be or weaker than what it should be. Clearly, we cannot say that because my t is way less than the critical t. Okay, but if somehow I made this number big enough, I mean, when I took the samples and tested them, if this number was such that this number turned out to be 2.5, okay, so this number was quite a bit bigger, or let's say even not 2.5, 2.21, okay, something bigger than that. If this number was 2.21, in other words, the average of this data was a little bit bigger, then it would have been significant. Now, in this case, if I calculated, that number is going to be 751.83. So if the average of the sample was even as big as this, only 1.83 bigger than the desired value, that would have been significant. And I should have said, yeah, these guys are stronger than what we are shooting for. But in this case, the difference between this 750.33 and 750 is not significant enough. So I say we are good. There is no significant difference between the samples and what we are shooting for. So whatever we have been doing is good. Keep doing it. Okay, so you see again, it's quality control, but this time I have no knowledge of sigma. I can only rely on S. So I have to calculate t-score and t-critical as opposed to z-score and z-critical. And in MATLAB, also remember that the t-score, right, the t-test can be given to calculate, as we did in one of my previous videos where I talked about the t-test, we can get the t-critical value. So hopefully this video shines a little bit more detail into these two different and yet closely related things, z-score, t-score, z-test, t-test, and I'm gonna see you in the next video. Thank you.